Sequence models used to be all about recurrence, processing data step by step. But what if we could process an entire sequence at once, understanding context across all elements simultaneously?
For years, the dominant sequence transduction models are based on recurrent or convolutional neural networks. They excelled at tasks like machine translation, but their sequential nature created a bottleneck for training speed and parallelism.
And these models typically used an encoder-decoder configuration, right? One part reads the input, another writes the output. But where did attention fit into that picture before the transformer?
Exactly. Before the transformer, attention was an add-on. The best performing models also connect the encoder and decoder through an attention mechanism to help the decoder focus on relevant parts of the input.
Then this paper dropped with a provocative title, "Attention is all you need." It implies attention isn't just an add-on, but the whole show. What was their core proposal?
Their proposal was revolutionary. A new simple network architecture, the transformer, based solely on attention mechanisms. They completely dispensing with recurrence and convolutions entirely, which was a radical shift for sequence modeling.
So no more step-by-step processing? Does dispensing with recurrence mean the model can suddenly process all parts of the input simultaneously? That sounds like a huge speed up.
That's precisely it. By removing recurrence, the transformer became more parallelizable and requiring significantly less time to train. This allowed for training on much larger datasets, which was key to its success.
But if it processes everything in parallel, how does it know word order? Doesn't cat chases dog mean something different from dog chases cat?
Excellent question, Maya. This is where positional encodings come in. While self-attention removes recurrence, the transformer still needs to know the relative or absolute position of tokens in the sequence. So before being fed into the encoder, each word is embedded into a vector of size 512. And to this embedding, we add a positional encoding vector. This special vector gives the model information about the word's position in the sequence, allowing it to preserve the order without relying on sequential processing.
This sounds like the foundation for many of the large models we discuss, like the visual transformers we explored in cases TCM 003002 and TCM 093004. The flexibility of attention really shines here.
It certainly does. The idea that the transformer generalizes well to other tasks is fundamental. But how does this attention-only architecture actually work? Let's build the intuition, starting with its high-level structure.
Let's start by looking at the transformer as a single black box. For machine translation, you feed in a sentence in one language, and it outputs the translation in another. Simple on the surface.
Opening that black box, we see an encoding component, a decoding component. This still sounds like traditional sequence-to-sequence models. What's fundamentally different inside these components?
The key difference is what these components are made of. The encoding component isn't just one encoder, but a stack of encoders. Similarly, the decoder is a stack of decoders, typically 6 of each.
So it's modular, with each encoder being identical in structure. We can even dive one level deeper. Each one is broken down into 2 sublayers. What are these layers doing?
The first is a self-attention layer. This is the core innovation. Imagine reading a sentence. As you process each word, your brain subtly connects it to other relevant words in that very sentence. That's self-attention. Now, where this analogy breaks is that your brain doesn't compute dot products or softmax, nor does it typically blend information into a single vector for each word. It's a computational abstraction of that focusing process.
So self-attention builds connections, but the second sublayer is a feed-forward neural network. Does that mean the outputs from self-attention are then processed independently for each word?
Precisely, the feed-forward layer does not have those dependencies between positions. This is crucial for parallelization. While self-attention creates connections, the feed-forward step processes each position separately.
Okay, so the encoder has self-attention and a feed-forward network. What about the decoder? Does it have the same structure, or is there something special about how it processes information for generation?
The decoder, like the encoder, has a self-attention layer and a feed-forward layer. But crucially, it adds a third type of attention layer, often called encoder-decoder attention, or cross-attention. This layer focuses on the output from the encoder stack.
So the decoder doesn't just self-attend to its own partially generated output, but it also looks back at the original input sentence encoded by the encoder. This is an attention layer that helps the decoder focus on relevant parts of the input sentence.
Precisely. While the decoder's self-attention helps it understand the context of what it has already generated, this encoder-decoder attention allows it to dynamically refer back to the source sentence for relevant information, guiding its next word prediction. It's how the translation system can ensure consistency between the input and output.
Let's use an example. If we have the sentence, "The animal didn't cross the street because it was too tired." When the model processes it, how does self-attention help it know it refers to animal and not street?
Self-attention allows the model to dynamically create a weighting for every other word in the input sequence relative to the current word. So when processing it learns to associate it with animal much more strongly than with street.
This sounds powerful. It's like each word is asking, who else here is relevant to me? But how does this dynamic weighting and association actually happen under the hood? What's the mechanism?
The core of self-attention is creating three distinct representations for each word: a query vector, a key vector, and a value vector. These are generated by applying three different linear transformations, multiplying the word's initial embedding by three separate learned weight matrices, one for query, one for key, and one for value.
Okay, what are the query, key, and value vectors? This is where the analogy gets a bit fuzzy. Are they like search terms, identifiers, and the actual information?
That's a good intuition. They are indeed abstractions that are useful for calculating attention. Think of a query asking, "What am I looking for?" A key saying, "What do I offer?" and a value being, "Here's the information I hold." However, it's crucial to remember that unlike a literal search system, Q, K, and V vectors for a single word are all derived from that same word's initial representation, just transformed differently. They don't represent independent entities asking and answering, but rather different aspects of the same input used in a computational matching process.
So the query asks and the keys respond. How does that interaction determine which words are relevant? What's the first computational step for this scoring?
The first step is to calculate a score for every other word against the current word's query. This score is simply the dot product of the query vector with the key vector of the respective word.
The dot product measures similarity, right? So a high dot product between query and key means those words are conceptually related. This score determines how much focus to place on other parts.
Exactly. After calculating all scores, we divide the scores by 8, which is the square root of the key vector's dimension, d sub k equals 64 in the original paper, to prevent extremely large dot products from pushing softmax into regions with tiny gradients. Then we pass them through a softmax function. Softmax converts these raw scores into probabilities that sum to 1.
The paper says this softmax score determines how much each word will be expressed at this position. So these normalized scores are our attention weights, the dynamic focus we talked about.
Precisely. The final step is to multiply each value vector by the softmax score, then sum these weighted value vectors. This combined vector becomes the output for the current word, incorporating information from all other words based on their relevance.
So that's how a single attention head works. But is one perspective enough? What if the model needs to focus on different types of relationships simultaneously?
You're anticipating the next major component, multi-head attention. Instead of performing a single attention function, the transformer parallelizes this process. It projects the Q, K, and V vectors multiple times with different learned linear transformations. This allows the model to jointly attend to information from different representation subspaces at different positions. It also helps make the computation of multi-headed attention mostly constant even with smaller dimensional QKV vectors.
So it's like having several different specialized attention heads, each focusing on slightly different aspects of the relationships between words. For example, one head might look for grammatical dependencies, while another looks for semantic similarity, all at once?
Exactly. Each head learns a different set of attention weights, and thus different ways of extracting information. The results from these multiple heads are then concatenated and linearly transformed to produce the final output for that layer. This significantly enhances the model's capacity to capture a wider, richer range of contextual information.
So the transformer isn't just looking up information, it's dynamically creating a context-rich representation for each word by blending information from the entire sequence and doing it from multiple perspectives. This is a fundamental shift.
With the mechanism of attention clear, let's look at one of its most impactful applications. The transformer laid the groundwork, but models like BERT showcased its true power in natural language understanding.
In 2018, Google introduced a new language representation model called BERT. The acronym itself tells us a lot about how it uses the transformer architecture.
Indeed, BERT stands for Bidirectional Encoder Representations from Transformers. The bidirectional and encoder parts are critical here. It's not a full encoder-decoder like the original transformer for translation.
We covered the transformer's encoder-only generalization to vision in case number TCM093004. So BERT uses only the encoder stack to build deep bidirectional representations from unlabeled text.
Precisely. The bidirectional nature means BERT can look at the entire context of a word, both what comes before and what comes after simultaneously. This is a huge leap from earlier models that were limited to left-to-right processing.
So BERT's innovation was to pre-train deep bidirectional representations on massive amounts of raw text, learning general language understanding before any specific task. That sounds like a powerful foundation.
It was. Once pre-trained, BERT could then be fine-tuned with just one additional output layer for a wide range of tasks, from question answering to sentiment analysis, achieving state-of-the-art results across the board.
This all sounds incredibly powerful, but are there any downsides or limitations to the transformer's self-attention mechanism?
Definitely. One major challenge is its computational cost. Calculating attention for every word with every other word leads to quadratic complexity with respect to the sequence length. For very long texts, this can become prohibitively expensive, leading to innovations like sparse attention or recurrent attention in later models. Also, while attention can capture dependencies, it inherently lacks the sequential inductive bias that RNNs had, necessitating careful design choices like positional encodings to provide order information.